Hey guys, welcome back to my channel, Math Sprint, and you are watching the third video of my calculus crash course. Today I'm going to be explaining inverse functions. Now, before we begin, make sure you're familiar with at least these concepts, which will be very important if you want to understand this chapter in calculus. So first, understand these concepts and then continue with this video. The topics to know are basic algebra, quadratic equations, polynomials, graphs of polynomials, how to plot a graph on a Cartesian plane, exponents and logarithms, differentiation and its fundamental rules, how to perform differential calculus on different functions, different types of functions, and implicit differentiation. Also, do note that for this chapter of calculus, I will only be working with real numbers and not imaginary numbers. So do keep that in mind. Now, inverse functions. Firstly, don't confuse the inverse of a function with the reciprocal of a function. In mathematics, they are not the same thing. Inverse functions, they're also called anti-functions, are functions that will reverse the process carried out by the original function. Basically, if we have any function f that maps x to y, then the inverse of f will map y to x. If the function is denoted by f, then the inverse function is denoted by f inverse. We use the -1 symbol to indicate the inverse. Now remember, do not confuse the -1 here with an exponent or reciprocal. Here, it does not represent that. Now, let's take a situation where we have f and g are inverse functions. That is, they're inverses of each other. And f of x is equal to y. Then logically, it follows that g of y is equal to x. We write that f inverse of x is equal to g of x, or f of x is equal to g inverse of x. And it follows from this understanding that g of f of x is equal to x, or also f of g of x is equal to x. So you could say that the inverse function returns the original value for which the function gave the output. You need to recognize when a function is to the power of -1 and when it refers to an inverse function. Many people have made mistakes confusing to the power of -1 and inverse functions. So it's important to understand this. So for example, look at the bottom of this slide. G of x is equal to sine inverse of x. This is not sine x to the power of -1 or 1 divided by sine x. If we want to say sine x to the power of -1, we need to put a parenthesis around the sine x and raise it to the power of -1. But for any number other than -1, we can put it as sine to the power of nx, and it will not indicate the power of an inverse function. If we want to talk about the power of an inverse function, we would represent it as sine inverse of x and raise the whole function to some power of n. To avoid confusion, some mathematicians prefer to add the prefix arc to a trigonometric function to represent its inverse. For example, y is equal to arc sine x is the inverse function of y is equal to sine x. Now, here's another important thing to remember. Inverse functions only exist for functions that are one-to-one for a given domain. Let's say we have a function f of x is equal to 2x plus 3. It has an inverse function because it is one-to-one for all real values of x. But for all real values of x, g of x is equal to x squared does not have an inverse function. If we have the function, say g, if we have the function g of x is equal to x squared on the domain x is greater than or equal to 0, then g has an inverse function. I'll be explaining how this works when I show you the graphs of inverse functions in a few minutes. Now, how to find inverse functions from one-to-one functions? So there are different ways generally to find the inverse function. Algebraic manipulation is definitely necessary, but remember, inverse functions only exist for functions which are one-to-one for a given domain. So let's go through a series of steps. Step 1, replace f of x with y. We do this because it's easier to perform an algebraic manipulation with single letter variables like y rather than entire function values saying f of x. Now, step 2, use algebraic manipulation or any other valid technique to obtain an equation for x in terms of y. Then the third step, replace x with f inverse of x and y with x. Don't perform these sub-steps in reverse order. That is, don't first replace y with x and then replace x with f inverse of x. You're not going to get anywhere. So let's do a sample problem here. F of x is equal to 2x plus 5. The first step, replace f of x with y. we now have y is equal to 2x plus 5. The second step, perform algebraic manipulation such that we have an equation for x. We subtract 5 from both sides and then divide the left-hand side and the right-hand side of the equation by 2. So we have now x is equal to y minus 5, the whole thing divided by 2. Now we replace x with f inverse of x and y with x, and we finally arrive at f inverse of x is equal to x minus 5, the whole thing divided by 2. Graphs of inverse functions. The graph of an inverse function is symmetrical to the graph of the original function about the line y is equal to x. This fact is true for all one-to-one functions, essentially. I want to explain here the reason that f of x is equal to x squared, why it has an inverse function for x is greater than or equal to 0. So take a look at the graph on the left. If you apply the horizontal line test upon the blue line, you'll find that the function is 1-to-1. So f of x is equal to x squared is 1-to-1 for specific domains only. Clearly, it's 1-to-1 for x is greater than 0, or x is less than or equal to -1, and other domains. The horizontal line test can be useful in finding the domains for which a function is 1-to-1. When a value is inputted into a function, an output is obtained. That when this output is plugged back into the inverse function, the original input is reobtained. So if we say we plug in x is equal to 2 into the function f of x is equal to x squared, we would obtain 4 because 2 squared is equal to 4. But if we plugged in the 4, that is the output, into the inverse function, f inverse of 4, because f inverse of x is equal to square root of x, we would obtain 2 again. So it follows from this understanding that the domain of a function is the range of its inverse function, and the range of a function is the domain of its inverse function. So if the domain of f is, say, x is greater than or equal to 0 again, the range of f inverse is y is greater than or equal to 0. And if the range of f is y is greater than or equal to 8 and less than or equal to 10, then the domain of f inverse is x is greater than or equal to 8 and x is less than or equal to 10. Derivatives of inverse functions. So now we're getting more into differential calculus. If a function f is invertible for a given domain, and the inverse function can be expressed as y is equal to f inverse of x, then dy by dx is equal to 1 divided by the f dash of y. So you essentially have to by heart this formula. It applies for all one-to-one functions which are invertible. Let's do a practice problem. Suppose f of x is equal to x to the power of 5 plus 2x cubed plus 7x plus 1. Our task is to find f inverse dash of 1. First, we should show that f inverse of x exists. That is to say, f is a one-to-one function. In this case, the derivative f dash of x is equal to 5x to the power of 4 plus 6x squared plus 7. And this function is strictly greater than 0 for all real values of x. So f is strictly increasing, and thus f is a one-to-one function. It's difficult to find the inverse of f and then take the derivative. So that's why we're going to use the formula that I showed you on the previous slide. So therefore, f inverse dash of 1 is equal to 1 divided by f dash of f inverse of 1. Note that to use this formula, we need to show that f inverse of 1 is, and the derivative of f dash of x. To find the f inverse of 1, we make a table of the values, plugging in different values such as x is equal to -3, -2, -1, 0, 1, 2, 3 into f of x. And we have to see what value of x gives 1. Now, let's omit the table right now and simply observe the fact that f of 0 is equal to 1. So therefore, we get that f of inverse of 1 is equal to 0. Now, when we plug this all into the formula, we get that f inverse dash of 1 is equal to 1 divided by f dash of 0. And since we know by using f dash of x is equal to 5x to the power of 4 plus 6x squared plus 7, we know that f dash of 0 is equal to 7. So therefore, f inverse dash of 1 is equal to 17. Now, let's move on to the derivatives of trigonometric functions. The first one, the derivative of arcsine of x. Take a look at the triangle on the left. First, perform implicit differentiation with this scenario, and you can conclude eventually that d of the derivative of sine inverse of x, or the derivative of arcsine x, is equal to 1 over the square root of 1 minus x squared. Now, the derivative of arctan of x. Again, here's a different scenario with different values. By the way, do note that we're able to calculate these different values for the hypotenuse and the adjacent sides by just taking one side as 1, the other side is x, and then using the Pythagoras theorem to eventually find the third side. So the derivative of arctan of x. Take a look at the triangle on this left again, perform implicit differentiation, and we eventually conclude that the derivative of arctan of x is 1 over 1 plus x squared. The derivative of arcsec x. Now again, here's a new triangle. It's a right-angled triangle. Perform implicit differentiation, and you can conclude that the derivative of arcsec x is 1 divided by x times the square root of x squared minus 1. So here's essentially a summary of the derivatives of the inverses of all 6 trigonometric functions. You might want to note these down or take a screenshot. I've arranged them in such a way that you might be able to draw parallels between some of them, so that way it'll be easier to by heart them. You might notice that the derivative of sine inverse of x is 1 by square root of 1 minus x squared, and for the derivative of arc cos x, it's just the negative of that value. And you can see these parallels here, where the lower functions are just the negatives of the upper functions. So here's some problems you might want to attempt. You can use these to determine if you've truly understood the concept or not. Pause the video and work on all 3 of these problems. I'll be showing you the answers shortly. All right, here are the answers. If you got them right, give yourself a big pat on the back. Otherwise, you may want to go through this video again and try to understand the concept better. Thank you guys. That'll be the end of this video. Make sure you hit that like and subscribe buttons to see my future videos in mathematics. Until then, stay tuned.